Hello everyone. Today we are going to continue our discussion of open channel flows. In particular, we are going to focus on deriving some formula, like kind of semi-empirical equations for uniform flows. So the first thing I'm going to do is define, and again, this is kind of like a reminder for you because we have already defined uniform flow, but just to talk about it in more details about what are uniform flows. Okay, so as you can see, a uniform flow is defined as when the derivative of the depth with respect to x, so x is in this direction, and this is y. So the derivative of the depth of the flow in the x direction is 0, right? So this means that your flow, your open channel flow, does not change its depth along the channel. Okay, so it has a constant depth along the channel. So this is achieved by when the energy loss by the viscous forces, so this is like the energy loss HL by the viscous forces, is balanced by the potential energy loss as it flows downhill, or S naught or S0. So when you're in the energy equation, when your the loss that is due to this frictional effects, due to the surface friction or viscous effects on the surface, is balanced by the potential energy that is lost when you flow from here upper elevation to a lower elevation, then you will get this dy over dx equals to 0, or your depth of the fluid is going to be 0. In other words, when in your energy equation S naught equals to S0, S naught equals to SF, then you will get y1 minus y2 should equal to 0. Okay? And this is, in this kind of situation, you will get a uniform flow. Okay? In case that yeah, so now I want to define some parameters that are specifically used in this type of flows, and one is what we call weighted perimeter. So as you know, the channel types, the cross sections can have different shapes, and in order to make a general formula for any type of cross section or any cross sectional type in the channels, for instance, we saw both rectangular and triangular channel types. We make a definition which is shown here as the weighted perimeter. So the weighted perimeter is defined as the length of the perimeter of the cross section in contact with the fluid. So this green line that is shown here is the weighted perimeter for this cross-sectional area of open channel flow. Okay, A here is the flow area, which is shown as these blue lines, and this green one is the weighted perimeter. Okay. So we make some assumptions in these uniform flows to be able to derive some simplified equations, and some of them we are going to talk about them like some semi-empirical equations. And one of the main assumptions is that first, as you can see here, the real velocity profile in this type of flow is going to look something like this, right? we have the no slip condition at the bottom, and so the velocity at the bottom should be 0, right? And then the velocity is going to increase as you go further from come further away from the wall. However, in this type of flow, for simplicity, we just assume that we have a uniform velocity profile. So we assume that we have something like this. So we don't have to account for the variation of the velocity as a function of y, right? So we don't have to kind of account for this variation of v as a function of y, and we can just say at each location the velocity of the fluid is going to be constant along the y direction. Okay, so this is the second assumption that we make, and the first assumption that we make, and then the second assumption is that we have a constant wall shear stress along the channel. So this tau w, or shear stress at the bottom of the wall, is going to be a constant value. Okay, so with these assumptions, we are going to derive two famous equations in open channel flow kind of literature. The first one is Chezy and Manning equation. So the first one is Chezy equation, and then the second one is kind of a modification to the Chezy equation, which is Manning equation. So both of these are kind of semi-empirical equations, especially the Manning equation is found from doing a series of experiments, but they both give a kind of a reasonable engineering results that we can use in many civil and environmental engineering applications. Okay, so let's start with deriving the Chezy equation. So for the Chezy equation, we have this open channel flow. Again, we have the uniform flow assumptions. So y1 at these two cross section, if this is like we have this control volume here, which is this dash rectangle here. So if this is section 1 and this is section 2, so y at 1 should equal to y at 2, because we have a uniform flow, and that's kind of a definition of a uniform flow. So the length of this control volume is L. The slope is theta. So here I have shown the we have V1 and V2. Again, V2 and V1 should equal to each other because we have continuity equation, and Y1 equals to Y2. And because Q1 from the continuity, Q1 should equal to Q2. And because y1 equals to y2, we have the same cross-sectional area, so we can say that v2 should equal to v1. And the other forces in this system control volume is, first is the shear wall stress, which we show as tau w times p. P is the perimeter in which the fluid is in contact with the channel, and L is the length. So this is gonna include all the area in which the fluid is in contact with the channel, and then we multiply all. This is gonna, so P times L is gonna be area times tau W is gonna give us the force, which is the frictional force, which acts in the opposite direction of the flow direction. And then we have also the weight of the water, which is shown here as gamma, which is rho g, the specific gravity, times the area, cross-sectional area of this channel, multiplied by L, which is the length. So this is gonna give me the weight of this fluid, right? This is like the volume, A times L. Rho g is rho is the density, and g is the gravitational constant. So this is going to give me the weight of the fluid, and we can having all these forces, Now we can write the momentum equation in the x direction. So here in the x direction, here we can say along the channel. So this is going to be my coordinate system here. So I'm writing this along the channel, the momentum equation along the channel. And then I have y here. Okay. So first I divide the weight into two components, one along the channel and one normal to the channel. So the component along the channel is gonna be w sine theta, which is this component shown here, and this one is gonna be w times cosine theta. Okay. So I will write the momentum equation in the x direction along the channel. So the sum of the forces along the channel is gonna equal to rho q times v2 minus v1. So these are from the momentum equation that we derived before. And because v2 equals to v1, you see, because we are in a uniform channel, so this should equal to 0, and so the sum of the forces should equal to 0. Okay. So again, I repeat it again. So sum of the forces should be rho times q, the flow rate, times v2. v2 is in this direction, minus v1. And the reason we have a minus sign here is because v1 is entering your control volume, and v2 is going out of your control volume. So this one should have a positive sign, and this one should have a negative sign. Right? This is based on the kind of convention we made when we drive the momentum equation. Okay. That the normal is always, for any control volume, is always outward of that control volume. So if you have any control volume like this, the normal is gonna be out of that. Okay. So rho q times v2 is gonna have a positive number because it's going outward, and rho q v1 is going to have a negative sign because v1 is entering your control volume. Okay. So this tells us that because this is v2 equals to v1, so the sum of the forces should be 0, and therefore we have no acceleration. So the flow is not accelerating, right? And this is kind of obvious because v2 and v1 are equal, right? So the velocity is not increasing. So I can say that the sum of the forces should be 0, and then I just write the sum of all the forces in this control volume. So first we have the hydrostatic pressure forces, so F1, which is here, which I'm going to show how you can calculate it, minus F2, which the pressure force here, minus tau W, which is the shear wall stress, multiplied by the area, which is the P. P is the wetted perimeter, multiplied by L, which is the length. So this is going to be the area. This is the area in which the wetted area, I would call, plus we also have this component from the weight of the fluid, which is W sine theta. Okay, so this equals to 0, and these two are hydrostatic pressure forces, and this one is viscous force. Okay. So now let's see what are these hydrostatic pressure forces. So what hydrostatic pressure forces for these two, this is Y1 and this is Y2, are two sections. We can calculate them. So it's going to be 1/2 of rho g y1, which is here, this value here, multiplied by this y1. So this is like the area of this. And F2 is going to be 1/2 of rho g y2, which is this one. And then multiplied by y2, this is going to give me the area of all these forces, okay? And since y1 equals to y2, because we are in a uniform flow, and this is like a uniform flow assumption, I can say that F1 equals to F2, right? This comes because we are in a uniform flow and y1 equals to y2. And as I said, tau WPL is the shear force on the fluid that is exerted on the fluid because of the friction at the surface. And so now that we have all these, we can substitute these here. So F1 and F2 are going to cancel out. So these two are going to be, because they are equal, so it's going to be 0. And we are only left with tau WPL equals to W sine theta. So equation 1 becomes tau W equals to W sine theta, which is the weight times sine theta, over P times L. The perimeter, wetted perimeter times the length. And then I can make another assumption. So S naught, if you look at the definition, is tangent of theta, right? So if this is theta, so S naught is this delta Z, this change in the elevation over L, right? This L. So this is Z. So delta Z over L, this is gonna be S naught, which is tangent of theta. And because in most open channel flows, this theta, this slope is very small, I can make an approximation that tangent theta is almost equal to sine theta. If theta and S naught are very small, I can make this assumption. So I can just write this here, that sine theta is almost equal to S naught. So I can write this down as tau W is almost equal to W S naught over PL. Okay, so now I can write what is weight. The weight of the fluid for this control volume is gonna be rho g, the density, times g, the gravitational constant, times the volume of this control volume, which is going to be area, the cross-sectional area, times L, right? So it's going to be gamma AL. And so I just substitute those definitions. So tau W is going to be gamma, instead of W, I'm going to write gamma AL. So it's going to be gamma AL times S naught over PL. And so I'm going to write this down as gamma times RH, make a definition, and I will talk about what that is, times S naught. So RH is defined as hydraulic radius and is the ratio between the area, the cross-sectional area, and wetted perimeter. Okay, so here, if I show you, so RH in this is gonna be this area of the flow over the wetted perimeter. Okay, so for this type of flow, as you can see, this is gonna be the hydraulic radius. So this is the definition for hydraulic radius that we use. And so we can just write this tau W, the shear wall stress, in terms of the hydraulic radius, which is RH, okay? And if you calculate, you will see that hydraulic radius is 1/4 of hydraulic diameter, Okay, so it's not 1/2 of hydraulic diameter, because here we have area. So I'm not going to calculate it. You can calculate it yourself, but this is the based on this definition, and you can find that the hydraulic radius is going to be 1/4 of hydraulic diameter. Okay, so now let's continue. So I want to make one assumption for finding this shear wall stress, and that is, for most open channel flows, they are very turbulent. They are in the nature, and the nature, most of these environmental flows are turbulent and have very high Reynolds number, so very large Reynolds number. And if you remember, this was the Moody diagram, right, where we had Reynolds number versus the friction factor. And in the Moody diagram, we had one part which was for laminar flow, so this part, and one for turbulent flows. So here we had the transitional regime, and then here the flow became very turbulent. So for very large Reynolds number, the flow becomes very turbulent. And if you remember, for all these cases that we had, like we had a lot of these kind of these type of like cases. So for very large Reynolds number, most of them became kind of flat, right? And they were not a function of Reynolds number for very large Reynolds number, and they were only a function of relative roughness length, which is epsilon over d, right? So for pipe flows, this was kind of the thing we had for the friction factor, right? So this was like the Moody diagram. So for pipe flows, the friction factor is independent of the Reynolds number for very large Reynolds number, and is only a function of epsilon over d, right? So this is something we found from Moody diagram, and we found it from experiments actually. So for such cases, we can say that tau W, or wall shear stress, is going to be proportional to the dynamic pressure, which is rho v square over 2, and is independent of viscosity, independent of Reynolds number and viscosity, okay? Because, so this is something similarly we can say for open channel flows, for this type of cases, and they're going to be completely independent of the viscosity of the fluid, right? So because Reynolds number is the fraction between your inertial and viscous forces, right? So here we can say this is going to be only dependent on the dynamic pressure and roughness of your channel, right? So the shear wall stress, the wall shear stress tau W, we can write it as K times rho v square over 2, the dynamic pressure, where K is a constant which depends on the roughness of your channel, okay? So this is an assumption I can make for very large Reynolds number flows for this type of open channels. And if I make this this assumption, then I can combine equation 2 and 3 together, and what I'm gonna get, combining equation 2 and 3 together, I can just write that K rho v square over 2 is gonna equal to gamma RH hydraulic radius times S naught. So I will just rearrange this. V square is going to equal to 2 gamma. I will put everything else here on the right hand side of this equation, 2 gamma over K rho times RH over times S naught. And then I will square root of this equation to get V. So V is going to be square root of 2 gamma over K rho times square root of RH times S naught. So see this here, this value is constant. This depends on the density. So this is actually going to be even simpler because gamma is rho g. So this is going to be a square root of 2 g over k. So it only depends on the gravitational constant and your roughness, your channel roughness, right? And for the gravitational constant, usually take it as 9.81. So it's only dependent on the roughness of your channel. So this is what we call Chezy coefficient. And we can write this equation as this. So this is going to be our final equation for a uniform flow. V equals to C, where C is the Chezy coefficient, which depends on the roughness of your channel, multiplied by a square root of RH, hydraulic radius, A over P times S naught. Very, very simple formula. So for uniform flows, for open channel flows, we can find their velocity very simply by only knowing the roughness of the channel, which will give us this Chezy coefficient, the hydraulic radius, which is the area of the your channel, and wetted perimeter, and also S naught, the slope of the channel. And by knowing this, we can estimate the velocity very simply by this equation. So this equation is known as Chezy equation, and Chezy was one of the first people who derived this equation, and therefore this equation is known as Chezy equation. Okay, so this we found this Chezy equation from, as I said, from the momentum equation along the channel, and also the assumption for a very large Reynolds number, which we found that the shear wall stress is going to be only a function of roughness and dynamic pressure. And made some assumptions about the velocity profiles and other things for uniform flow. And we found that RH is V is a function of, here we found that we found that the so V is a function of RH to 1/2 and S naught half, right? So after doing some experiments, this relation between V and S naught, which is the bottom slope of the channel, to power 1/2, was validated. Okay, so there many experiments were done, and then when we compared the velocity of the channel with the bottom slope of the channel, we found this relationship actually is valid. Okay, but after doing a series of experiments, it was found that V is actually a function, or varies as a function, of RH to power 2/3 and not RH to power 1/2, which is what is in the Chezy equation, right? So it was found that V is actually a function of hydraulic radius power 2/3, not 1/2, right? So it's kind of close to this approximation, but it's a little bit different. So as you can see, this led to what is we know as Manning equation. So Manning found this from a series of experiments, and so we changed this equation from C times RH, hydraulic radius, square root of RH times S naught, to this RH to power 2/3 times S naught to power 1/2 over N. And N is Manning resistance coefficient, or what we know mostly as Manning's N, right? So this Manning's N, or Manning resistance coefficient, depends on the roughness of the channel, and we will talk about it in the next slide. But I just wanted to say that this is the Manning equation, which is kind of the modification of Chezy equation based on some experiments. So based on some experiments, series of experiments, we found that V is actually a function of RH to power 2/3 and not 1/2. So this is the main equation we typically use in open channel flow systems. It's very important and famous. And as you can see, by knowing N, which is a function of the channel type, which we will show it later, S naught, which is the slope of the bottom slope of the channel, and also the hydraulic radius of your channel, you can find the velocity of the open channel based on this Manning's equation. And this is very important equation in open channel flow system context. Okay, so in the next session, I'm going to talk about this Manning resistance coefficient and how we find this. We have a table for it in the book. And after that, we are going to solve two examples of Manning's equation. One for finding the determining the flow rate, and the other one for determining the normal depth in open channel flow system.